Oh, okay. So good morning, everyone. So yesterday and today we were discussing a lot about different treatment technologies. We are also at the same time discussing about the regulatory values that are pretty low. We're also discussing that most of the time short-change PFAS are not able to destroy, to remove from different treatments. And that's actually kind of the introduction for this talk. Today I will discuss about PFAS transport and deposition through rainwater. So the agenda for today, I will start discussing about what is the definition of PFAS background and key considerations for that. And then I will continue discussing a little bit about regulatory. We already discussed a lot yesterday and today in the morning. And then I will follow with discussing about transport and deposition pathway of PFAS in a case study, like looking on PFAS fingerprinting in rainwater. And I will finish with a couple of conclusions and recommendations. Okay, let's start at defining background. So what is background specifically for PFAS? So those are concentrations found in the environment, not affected by site-related releases. So often when we discuss about background, we're referring, natural occurring compounds, like for example, metals. But for PFAS, we know this is anthropogenic. But we have to start discussing about PFAS background because those compounds are widespread because we use it basically in almost every single commercial product. These concentrations can come from local sources like nearby factories or widespread sources like coming from air deposition. A couple of considerations we have to think about is that we are finding PFAS in areas where there is not even human activities, but why is that? Well, we all know that PFAS are really mobile compounds, and they are not only one single compound, right? We are discussing about more than 15,000 compounds, and even more every time we start looking at definition of PFAS. Those compounds' behavior in the environment change depending on the carbon numbers, depending of they are fully fluorinated or partial fluorinated, depending on the functional group that they may have. They are very persistent. We know that because the carbon and fluorine bonds. They can be detected in remote areas, and they are basically found everywhere, right? In fish, tissue, and polar bears. They are found in snow and also in precipitations. So they are widespread, which complicate background determinations. And those background concentrations could actually approach or exceed regulatory values. So the current regulatory values for federal and states are pretty low. So we are discussing right now for federal, we have the EPA regional screening values for PFOS of 0.2 nanograms per liter, and for PFOA it's even lower. We have 0.0027 nanograms per liter, which most of the time could be below analytical detection limits. And also we have MCLs values for drinking water, which may be around in the range of 4 to 10 nanograms per liter for a couple different PFAS. And for the states, the regulatory values change. Some of them could be actually below the federal values, and some of them could be higher than the federal values. So PFAS can move to the atmosphere coming from different sources. A couple of them include industrial stack emissions. We also have the blowing foam and also surface water mist. There is different transport pathways, and this is basically depending on the class of PFAS. So we have, for example, long-chain PFAS that probably will attach to particles and foam. But we also have PFAS precursors such as the fluorotellular alcohols or short-chain PFAS that will transport by gas phase. So once in the air, then they will come back to the ground by direct deposition of the aerosols or particles, or they could also come by rainwater precipitation. So again, the mobility of the PFAS will depend on the class of the PFAS. We all know that a sulfonic acid have a higher organic carbon partition coefficient than carboxylic acid. So because of that, we will expect that carboxylic acid will be the PFAS that will be found mainly in rainwater. So now we are going to start deeper in the data. So because of that, we understand that PFAS is actually widespread, it's everywhere. We did a metadata evaluation of peer review studies. We compiled more than 500 samples that cover approximately 12 different states. The data have very low detection limits, and also the analytical suite is more than the 40 PFAS detected by the regular EPA method 1633. The green color here in this figure are basically the states that were evaluated. Basically, most of them are in the east area of the United States, except for Wyoming. So looking at the data now, we have the PFOS was detected in 4 different states. In these 4 states that you can see highlighted in dark green, PFOS exceed 4 nanograms per liter MCL. Those are basically in the state of North Carolina, Michigan, Wyoming, and Ohio. So Wyoming is a rural state, so they have very low industrial activity, but still the values are actually exceeding the 4 nanograms per liter MCL. In rainwater. For PFOA, we also found that around 8 states exceed the 4 nanograms per liter MCL, basically including the states of North Carolina, Vermont, Michigan, New York, Maryland, Ohio, and Delaware. Again, the combination of those states, we have rural, urban, but also some states where they have like some industrial activities. So there is no specific trend of what is moving PFAS to the rain. So before we were just comparing the data and looking at any exceedance to the 4 nanograms per liter for PFOA and PFOS. Right now we are looking at real data, so real values. So here we can see what is the total PFAS concentration, which is approximately 3,000 nanograms per liter. This is just rainwater data. We can see that the highest total PFAS concentration was in Delaware, then followed by Ohio, Wyoming, and Maryland. But we also can see that the green color in the pie plots are actually the dominant PFAS, which is trifluoroacetic acid, with the highest concentration of more than 2,000 nanograms per liter. So theoretically, TFA is a short-chain PFAS carboxylate because have a carboxylic group, and also because have 2 carbons attached to fluorine. But there is still a lot of controversial about PFA be PFAS, but also PFA to be natural occurring or is actually anthropogenic. For this presentation, we will exclude TFA just to look at the other PFAS involved in rainwater or detected in rainwater. We can see that the concentration decrease in rainwater decrease a lot. So we can have a total PFAS concentrations around 300 nanograms per liter. The highest was in Ohio, followed by Maryland and Delaware. We can see that there is a couple of states, basically North Carolina and Wyoming, where PFOS, a sulfonic acid, which basically will prefer to be in soil, is the dominant compound in the PFAS profile with concentrations up to more than 100 nanograms per liter, which you can see is pretty high, higher than the MCLs. We also can see that GeneX, like a kind of new compound, was found in 5 different states, and also exceeding their regional screening values of 1.5 nanograms per liter. So looking what is the PFAS composition, we were discussing before that we are expecting that carboxylates will be present in rainwater because they are more mobile. And that's actually what the data shows here. So the frequency of detection for the PFAS in groundwater by class is basically 68% was carboxylates. Only 11% was sulfonates, and then we have less than 10% between fluorotelomers, electrochemical fluorinated precursors, and also PFAS replacement, which include GeneX and Aldona. In those carboxylates, in the carboxylate group, we can see like a very wide range of carboxylic acids coming from 2 carbons to more than 12 carbons. Basically, the higher frequency is for PFBA, which is a C4 to C10 carboxylates. And the reason why usually TFA and C3 carboxylates are not detected is because they are pretty kind of new in the quantification methods. Otherwise, probably will be also pretty high and detected frequently in rainwater. So now we are looking a little bit deeper to the data. So we are presenting here 2 different case studies. The figure here is from Ohio. There is 5 different locations where rainwater was collected, as we can see here in this red circle. The highest concentration was in Worcester, with a concentration up to 600 nanograms per liter. This area is a combination of urban and rural areas. So the pie plot here is just from the highest area with the area with the highest concentration. If we are looking on the PFAS composition, we can see that it's basically carboxylic acids, short chain PFAS. We have C4 PFBA with concentrations up to more than 100 nanograms per liter. We have C5 also with concentrations around 300 nanograms per liter. So the PFAS composition is basically 98% of just carboxylic acid and basically short chain PFAS. In this figure, we try to plot the locations where groundwater was collected, but also the potential PFAS sources. So we use EPA data to plot those locations. So we have 4 different categories. The federal here is basically including Navy, Army, and Air Force installations. We have also producers, which include facilities like 3M, DuPont. We also have airports, and an additional category which include industry, which is basically any industry that produce or use PFAS in their production, including painting, textiles, fire protection companies. So the green dots here is basically, distributed in the whole state. So looking at specific PFAS profile for these 5 locations. So before we were just focusing in one single location, which is the pie plot here. But looking at these 5 different locations, we can see the PFAS profile and how it is different between the locations, or it's similar. So This 3D plot is part of our fluorescence tool where we are doing fingerprinting. This 3D plot is the way we are organizing the PFAS data, which include basically the 40 PFAS that is included in the 1633. In the x-axis, we have the carbon number from 4 to 14, and then in the y-axis, we have a different PFAS class. So in the top, we are grouping together all the PFAS precursors, so electrochemical fluorinated precursors are in the top, and then followed by fluorotelomers. And then we have this line here where you can see all the bars actually are carboxylates. And then next to the carboxylates group, we have the sulfonates, so the terminal PFAS. And below, in the bottom, we have basically all the PFAS replacement, which include GeneX in this 3D plot. So if we are comparing these 5 different locations and compare the PFAS profile, we can see the PFAS profile is very consistent. So all the locations, even that they are not necessarily close to each other, they have carboxylic acid from 4 carbons to maybe 9, I cannot see very well here, but around 9 carbons, and we also have detections of only PFOS for the sulfonic acid, and we have detection of 1 PFAS replacement, which is GeneX here. So it's very consistent. So if we go back to the previous figure, we can see that the locations were not close to each other again. Some of them are actually rural areas, others are very close to actually more industrial activities, but the PFAS profile is pretty consistent between those locations. So now, in this case, we are looking at New York data. For New York, we have, again, 5 different locations. Again, we have the PFAS source categories here, similar to before. We can see a lot of industrial activities near to the ocean. We can have, again, a variety of different geographic areas, urban, rural areas with a lot of industrial activities. The highest concentration of PFAS in rainwater was detected in Ithaca. And the PFAS profile in Ithaca is, again, basically a lot of carboxylic acids. Most of them are short-chain PFAS. We have a C5, C3, and so also PFBA is also here. So basically, again, more than 90% of the PFAS profile is just carboxylic acid with short chain. Again, let's start looking at the data by location. So before, for Ohio, the PFAS profile for the 5 different locations was very similar. Here we can see like there is, the locations have a very different PFAS profile. We have first Ithaca, where basically we have a lot of carboxylates, including short chain, a couple of long chain PFAS, but basically is a lot of carboxylic acid of short carbon, a few carbons. But we, in going in the different locations, we can see like these specific locations have a carboxylic acid from 4 to more than 8 carbons, probably, I cannot see very well, but 12 carbons probably. We also see that they have PFOS, and there is the presence of precursors also in rainwater. Here in Albany, we have 2 different locations in Albany, one close to downtown and in the other one a little bit farther. Even that in the same city, the PFAS concentration in rainwater was not similar. We can see that in these specific locations, we mainly have long chain carboxylic acids and the presence of long chain sulfonic acids like C6 and and C9 or C10 sulfonic acids. But here in downtown Albany, we have like more carboxylic acids, including short chain, but also long chain carboxylic acids. And only PFOS was detected. A couple of PFAS precursors, basically electrochemical fluorinated compounds, were also detected in rainwater. So this tells us that, it's important to know what is the industrial activity or what kind of PFAS sources you may have around during your installation, because that could affect your PFAS profile. So this is a summary of all the data. We have a little bit more data, but because of the time, I'm not presenting here. You can see like there is not, the PFAS profile is not consistent. So we have states, for example, in the top where we have like a lot of different PFAS, including carboxylic acids, sulfonic acids. We have a lot of PFAS replacement. We also have a lot of different PFAS precursors, including electrochemical fluorinated compounds, including fluoropolymer compounds. But in these three different states, even that we have like different PFAS classes, the concentration was pretty low. I think it's below 10 nanometers per liter in for most of these PFAS. But then if we look just to the next three plots, we have Delaware. I cannot see the states here, but we have three different states which concentrations are pretty high, around 1,000 nanometers per liter, and those are actually including regulated compounds like PFOS and PFOA. And again, the PFAS profile is changing depending on the state. It's also changing depending on the proximity of this state or these cities to industrial activities, to federal installations, or airports. So in conclusion, we did an evaluation of more than 500 different samples covering like 12 different states to try to understand what is the PFAS concentration in rainwater. We actually found that a couple of these concentrations exceed MCLs and a couple other regulatory values. We confirmed that short chain PFAS are the PFAS that are actually present the most in the PFAS profile in rainwater. Comparing with sulfonates, sulfonates probably, the presence of sulfonates in your data may indicate basically like industrial sources nearby those locations. And so these days we are getting a lot of requests from our clients to do PFAS background evaluations. And the main recommendation that we actually say to our clients is that we recommend definitely background studies if you have a stormwater monitoring component in your site, if you know of industrial sources nearby, if you have groundwater that is shallow, if you have soils with low organic carbon, or there is like anomalous data that cannot be explained by, as a PFAS source release. But we also recommend to not only collect rainwater data, it's important to also collect soil data, surface water data, or groundwater data to understand better what is the PFAS background in different media. With that, we'll...
Okay, there's time for a few questions, please. Please.
Well, basically, you're saying that local sources of PFAS are contributing to these different regions, and this is not a large atmospheric contribution that's coming from, let's say, other countries that are still manufacturing PFAS.
Good, because we can see here Wyoming have pretty high concentrations, and the highest concentration is for PFOS, which is actually could be mobile sometimes. But Wyoming is a rural area. It's not like a lot of industrial activities. So that could be coming from a different states just because of transport, long-range transport.
Yeah, I mean, my understanding, and I just look at a recent paper that Dan Bryant published where he looked at soil concentrations throughout the Northeast, and they're very consistent with atmospheric concentrations, but not from local sources. I mean, a lot of these compounds are not terribly volatile. PFOS is not volatile. You don't expect it to be volatilizing. It's got to come up on a particulate of some type.
Right. Could be attached to foam, or could be attached to particles.
So if you look at atmospheric chemistry, which is a much larger scale issue, there are still plants at large scale making PFAS in China and some other areas. And the reason you're getting up to the Arctic and all these areas is because there's so much of that material that gets up into the atmosphere and then gets deposited. So I don't know that I agree with your hypothesis that these are local sources, and I think your data show that, in fact, this is a very non-regional issue it's coming, whether it's Wyoming, a lot of that has to do with how the atmosphere is transporting around the country from other places.
Right, so we actually doing evaluation about that. When you mentioned about, some PFAS coming from China, we have a couple of clients actually interested on that, to know what is the contribution for this country to nearby locations. Right. Yeah, we're doing that.
So with that, can I ask if you guys evaluated how much of an impact the waves crashing against the rocks and putting PFAS into the air had on the study, because they just had a study come out saying that, waves crashing along the rocks from the ocean can put as much as a chemical stack.
Well, we are not doing the evaluation yet, but we are actually start doing some measurements about max flux to understand what is actually the contribution of rainwater to the environment. Since, rainwater is seasonal, so we can actually, or those studies can be only captured like some specific or a small range in the in the whole year. We actually need more studies to evaluate what is the PFAS variation over the year to understand what is the mass of PFAS going in the environment coming back from rainwater. So, and it will also change depending on the state, because rainwater is also depending on different locations.
Okay, thank you very much. Our next speaker